We continue our consideration of how to analyze continuous variables by looking at analysis of variance. In this lecture, we shall introduce analysis of variance, otherwise known as ANOVA, as a solution to the multiple comparison problem, where conducting numerous t-tests inflates the type 1 error rate. In this lecture, we explain the fundamental concepts of between group and within group variation, demonstrating how their ratio forms the basis for the f-test. We shall detail the necessary data types, the assumptions, and the step-by-step calculation of sum of squares, degrees of freedom, and mean squares. We shall also cover the interpretation of a significant ANOVA and the role of post-hoc tests to identify specific group differences. Consider that we have multiple group comparisons to be done. We're comparing 4 groups on a particular variable. So for example, we have 4 groups consisting of those who took captopril, digoxin, both drugs, or no drug. And the effect that we're looking at is the effect on ejection fraction in heart failure. If we were to use the t-test, it will require us to carry out 6 t-test comparisons. So we compare group A with group B, we compare group A with C, A with D, B with C, B with D, and C with D. This would also increase the probability of committing a type 1 error. And this is the problem with multiple test comparisons. Each test is based upon the probability that the null hypothesis is true. So each time we conduct a test, we run the risk of committing a type 1 error. Therefore, for multiple t-tests, the rate of error would increase exponentially by the number of tests that were performed. As an illustration of that, the rate of type 1 error is given to us by the formula we see, which is 1 minus alpha raised to power n, where alpha is our significance level and n is the number of test comparisons. So in this our example, where we would have 6 comparisons, the chance of a type 1 error is 26.5%. Therefore, we have only 73.5% confidence that the difference is true. As we all know, this rate or level is too low for our considerations. So what is to be done? Well, this is where analysis of variance helps us. Analysis of variance answers the questions: do these groups differ from one another? In other words, do the group means differ from one another? However, ANOVA does not tell us which pairs of groups are different. So for us to determine which pairs are different, it will require us to do post-hoc statistical tests. So therefore, the workflow for comparing multiple groups that are greater than 2 requires us to first do an analysis of variance to ask the question whether the group means differ from one another. And only if the answer to that is yes, do we then go on to do the post-hoc test. What do we require to do an ANOVA test? We require independent variables that are nominal. Thus, we require treatment groups, or factors as they are sometimes called, that are nominal. The one-way ANOVA means that there is only one independent variable. The dependent variable has to be continuous. That is to say, mean values can be calculated. So again, the independent variable has to be nominal, and in the one-way ANOVA, there is only one independent variable, and the dependent variable that we're interested in is continuous. This is what is required for us to do what is known as the one-way ANOVA test. There are certain assumptions for us to be able to do the one-way ANOVA test. It is a robust test. Even if assumptions are not rigidly met, the results may still be close to the truth, especially if the groups are of equal sizes. Nonetheless, the assumptions that we are interested in for us to be able to do the analysis of variance is that the groups should be mutually exclusive, so they should be independent of each other. They are not correlated and they are not paired. And the dependent variable should be normally distributed. The other assumption is that the groups should have equal variances, what is known as homogeneity of variance. So the variances have to be equal. What are the sources of variance that we can encounter? According to our null hypothesis, all the groups are equal and they are drawn from the same population. That is to say, the group means are identical. Scores may vary from each other in their own group, and this is known as within group variation. Groups may vary from each other, and this is known as between group variation. Together, these two types of variation, within group variation and between group variation, add up to the total variation in our data. The variance is used in statistics to measure variation rather than standard deviation. The variance of each group is measured separately. Then all the subjects are lumped together and the variance of the total group is calculated. This is the first step towards determining if the groups are different. And the reasoning is very simple. If the overall variance is about the same as the mean variance of the separate groups, the means of the separate groups are not different. Again, if the overall variance, that is the total variance, is about the same as the mean variance of the within group variation, then it means the means of the separate groups are not different. This graphic here illustrates that concept for us. We have the three groups plotted, and we find that each of these three groups has the corresponding group mean. And then we have the overall mean of all three groups combined, which is known as the grand mean. Within each group, you have your within group variation, and between the groups, we have what is known as the between group variation. If the within group variation and the total variation are equal, there is no between group variation, because the combination of within group and between group is the total variation. When the between group variance is greater, that is statistically greater than the within group variance, then this suggests to us that the means of the groups must be different. So in circumstances when the group variance is greater than the within group variance, then it certainly suggests to us that the groups must be different. If the null hypothesis were true, we will find that the groups will overlap to a large extent, and the within group variation is going to be found to be greater than the between group variation. And this is what we see in this graphic here. The within group variation becomes greater than the between group variation. And so this tells us that really these groups are not that different. If the null hypothesis were false, the groups will show very little overlapping, and the distance between the groups will be greater. That is to say, the between group variation is going to be found to be greater than the within group variation. And so this tells us that the null hypothesis is false. And so these groups, there is a difference between groups. So how do we measure this variance? The sum of squares is the sum of the squared deviations of each of the scores around a respective mean. And we see the formula for calculating the sum of squares. It is the sum of the squared deviations of each of the scores around a respective mean. The sum of squares. Let's look at some worked examples. So we have three groups: group 1, group 2, and group 3. And these are the raw scores. The mean for group 1 is 2, the mean for group 2 is 5, and the mean for group 3 is 8. If we lump everything together, we find that the grand mean, or the mean for all the groups, is 5. For each of the individual observations, we now calculate the deviations from the group mean. Of course, simply summing these deviations will result in 0, which is not useful to us. So what do? We square the deviations, and thus we arrive at the last column. And by the time we sum up the squared deviations, we have a total sum of squares equals 60. And so this is the total sum of squares. The total sum of squares represents the basis of the null hypothesis that all the subjects belong to one population, which is described by the grand mean. We can repeat this for each of the groups separately. So for group 1, we have a sum of squares that is equal to 2. For group 2, we have a sum of squares that is equal to 2 again. And for group 3, we have a sum of squares that is equal to 2. So if we add up all this, and this is known as the within sum of squares, it gives us a within sum of squares of 6 that represents the portion of total variation within groups. And so, recall, we just calculated the total sum of squares, which gave us a figure of 60 and represents the overall variation. And we just calculated the within group, the within sum of squares, where we got a value of 6. And this represents for us the total variation within the groups. So we added up the total variation within the groups. And so remember, we had said that the overall variation is given to us by summing the within groups variation plus the between groups variation. So we can now calculate the between group sum of squares. And the between group sum of squares is given to us like this. So the group mean minus the overall mean, and then by the time we add up everything, we have 54. Bear in mind that the between group sum of squares is calculated by adding up this, what we got, and this is weighted by the group sizes. That's why we have SSB equals SS1, which is given to us by 3 times 9 plus 3 times 0 plus 3 times 9. So the figures there, the 3 we see there, is the group number. So this gives us a total of 54. So what does that tell us? The between group sum of squares We got 54. So we have a summary table. And so if we look at our summary table, you can see here that the between group is 54, the within group is 6, and the total is 60. So these are all the figures we still got. As you can see, 54 plus 6 gives us 60. So we arrive back at our total, which we had already calculated earlier. And then the degree of freedom for the between group is 2. The degree of freedom for the within group is 6. And then we have the mean sum of squares and then the F statistic. So how are these figures derived? If you look at it, it's easy to infer how they are derived. So for example, looking at the first row, the mean sum of squares is given to us by the first column divided by the second column. So 54 divided by 2 gives us 27, 6 divided by 6 gives us 1. And the F statistic is given to us by the ratio of the between group variance and the within group variance. So we have 27 divided by 1, and so our F statistic is 27. And this is found to be less than 0.05 at that portion. So this is just the overall representation of an ANOVA table. So oftentimes when we look at our statistical output, we see something similar to this. And this shows us the relationships between these things, right? So the degree of freedom for the between sum of squares is given to us by k minus 1, where k is the number of groups. And then within is given to us by n minus k, where n is the total number of observations. And so we can see how these statistics are related. The degree of freedom for the between group variance is equal to the number of groups k minus 1. The degree of freedom for the within group variance is equal to total number of subjects n minus the number of groups, so n minus k. And the mean square, the mean of the sum of squares or mean variance, is the sum of the squares divided by the degrees of freedom, as we see. So in testing the group difference, to determine whether the between group difference is great enough to reject the null hypothesis, we compare statistically to the within group variance. And so the F statistic is given to us by the between mean sum of squares divided by the within mean sum of squares. The F statistic represents the ratio of between to within variance and is calculated as the between mean square divided by the within mean square. Interpretation of the F based on the F distribution indicates to us the critical values of F, knowing the degrees of freedom for between and within mean squares. So an F ratio greater than 5 is usually significant. So how do we interpret it? When the ANOVA value has a p-value less than or equal to 0.05, it is said that the categories are significantly different. Otherwise, it is not. The post-hoc test becomes important when the p-values indicates that the categories are significantly different. And what the post-hoc test does for us is that it helps us to be able to identify which of the groups are significantly different from the others. When the ANOVA leads us to reject the hypothesis of no difference among group means, the question that arises is to which pair or which pairs of means are significantly different. Often the comparisons of interest are specified before looking at the actual data. In this case, comparisons based on two sample t-tests could be considered appropriate. Often the case that comparisons of interest are specified only after looking, often the case is that comparisons of interest are specified only after looking at the data, or if there is a desire to carry out significance test on all pairs of group means. So we're basically talking about the post-hoc tests. And so there are different ways that the post-hoc tests are done. Common methods include the Bonferroni t-test. We have the Tukey's honestly significant difference. We have Schiffer's procedure, Newman-Kurl's, and Dunet's procedures. So all these are options. We shall not go in detail into this because this is beyond the scope of our lectures. However, in the statistical software, once you carry out this test, you will see options to be able to do post-hoc test, and we shall cover this during the practical sessions.